Hey everybody. So what we're going to do today is we're just going to go through a couple of examples of exploratory data analysis. And the first thing we're going to do is initialize these code blocks and import this data from these four different data frames that are loaded. And the first thing we're going to do is the variable MA, which is maternal age, from the births data set. Okay. And I've included some links to the descriptives and outliers code blocks that we need. And I'm going to pause the video for a second while I go to those links and copy paste the code blocks we need. Okay, so I'm back. And so we're going to start off here in this example um, with the descriptive statistics. Okay. And I'm going to have to change this, right? This is going to be maternal age. Okay. And then the variable has to switch to MA. Sorry, not WMA. MA. Okay. Change the W to the MA. Change the W to the MA. Change the W to the MA. Sorry, not mama, just MA. And again, copy this into the print part of the cat function. And so we can see. And looking at the mean and the median being 1.23 units apart and the standard deviation of 0.85, right? The first analysis that we're going to write is that the difference between the mean and median is greater than 1/10 of a standard deviation, right? Make that a markdown cell. And the mean is greater, thus we expect skew and outliers to the right. Okay, well then let's, this is age. Okay, I'll just add maternal in front of age in the print part of the statement here. And then I have to switch to the MA variable. So I'm going to change age to MA in all of these places. I have to scroll over. Why? Because it needs to be included over here, down here. MA. I've tried to switch all the ages to MA. There's a lot in this particular command block. Do I have the MAs? The MAs, I believe so. Okay. And just double checking, MA, no age. I'm looking to make sure that there's no age left over. It's all MA. And this is kind of strange. We have a lot of outliers to the right. So we do appear, right? So we seem to have confirmed our suspicion that there may be outliers to the right. It appears we have a lot of outliers to the right. And we notice that when we do it numerically, we're getting nearly 60 outliers to the right and only one to the left. And the box plot is showing a couple to the right and a couple to the left. So sorry, I've got to switch to Markdown. All right. And let's jump on to the maternal age and we'll look at the shape. Okay. So what do we do there? We're going to do histogram of MA, right? And we're also going to look at a density plot. So plot density MA, not histogram, I'm sorry, it's just hist. And the histogram looks approximately bell-shaped, but we do see that there is a clear skew to the right. The tail to the right is longer. So we see skew to the right. And again, since the main part of the graph, the mean and the median, the middle of where all the data is piling up, um, it's in this data set, it's a lot easier to have outliers over here to the right. Why? Well, the tail is longer to the right, and there's just not that much of the distribution to the left of where the majority of the data are. So we're going to expect to find any outliers over here. Okay. And the density plot is going to show much the same thing when we scroll down. And we see, yes, there is some evidence of a bell shape, but the tail to the right is longer. So what is our analysis there? Our analysis is that we have approximately normal distribution with a skew to the right. Okay. And we are going to do one final thing. We're going to look at a box plot. This needs to be marked down, and let's do box plot MA. And again, we confirm what we saw before, right? We have skew to the right. The above here, right? These are the larger numbers. If this is the x-axis, these are further to the right along the x-axis. We're doing a vertical box plot, so it's above, right? But the skew is technically to the right. And an approximately normal distribution. Okay, good for us. Let's jump into the next example. And what is our next example? Our next example is the delay, the minutes of delay from these United flights. Let me see what we named it. We have it, the name of the file is United. Okay, so we're going to do an exploratory data analysis for United. Right, and what am I going to do? Well, one of the first things I'm going to do is grab this descriptive statistics, right, and changing this United flight delays. And I need to change the MA to United. Copy paste that so this goes a little quicker. MA to United, MA to United, MA to United. I think Python has fallen asleep. Let's rerun this to make sure that everything is loaded how we need it to be. And it is not liking United. Let me see what we did. Oh, United has just pulled in a data frame. And so what? Oh, I see. This is what we want. We want delay. And that's going to be the data frame. But the delay column from the data frame, that's what I did incorrectly. Okay, so instead of United, what we want is delay. Apologies, that's easily fixed. There we go. That's the data vector that we have. And there we go. You can see nicely the descriptive statistics are laid out for us. Okay, So we look at the standard descriptives, and you can see that I've copy pasted the outliers block from above, and we'll look at that in just a second. The first thing to notice here, right, is that the median is 2 and the mean is 16.7, all right? And even with a standard deviation of 39.5, a tenth of a standard deviation is 3.95, which is clearly less than the difference here. So what are we seeing? We're seeing skew to the right. The mean is greater, much greater than the median. And so therefore we're expecting pretty strong skew to the right, outliers to the right. All right. And we see that when we look at the outliers. You can see there 607 outliers to the right. If we use the two standard deviation rule, notice that the box plot identifies over 1,500 outliers to the right. We have none to the left, right? So what is our analysis? At the moment, our analysis is there appears to be massive skew to the right and many outliers to the right with no outliers to the left. Okay, so we can just, take the appearance of skew and outliers to the right with us. And right, so the next thing that we want to do is we want to do shape of the delays uh, from United Flights. Okay, and so of course we'll do a histogram of delay. And yes, we can see immediately what's going on. A much longer tail to the right. I am going to try brakes equals 20. Why? Just to see if we can see a little more granularity. Not getting much luck there, so I'm trying brakes equals 30. It's just that these bars are so close to the x-axis. We have so few of these flights, which makes sense. A 300-minute delay is 5 hours, right? So not many flights get delayed that long. So again, you can see, as we've said before, this is kind of guess and check, right? We're gonna put enough brakes or few enough brakes that we can see the shape. We see the massive skew to the right. We don't see much evidence of a tail to the left. So at the moment, we're not in approximately normal land. We're in, this is massively skewed to the right. Okay, so let's take a density plot. So plot density delay. This will give us a little more granularity. Okay, now in the density plot, we're finally seeing a small tail to the left and this huge tail to the right, where these flights that are delayed for 4, 5, 6 hours. And there are a couple of them, but there's not very many. Okay, so do we have approximately normal? Is this enough of an evidence of an emerging tail to the left to be approximately normal? And that's a judgment call, and I'm going to say no. So my analysis of the shape is, let me just put skewed hard right and not normal. Okay, there are going to be some people who say, well, there's a little bit of evidence of tail to the left, so maybe that can be considered normal. At the moment, what we know is that it's massively skewed to the right, which makes sense, right? The majority of these flights are between, 0 and 30 minutes delay, which makes sense. Most flights are reasonably close to the time they're supposed to arrive, right? And then there's this small percentage of flights that are 100 minutes delayed or more. And there's almost no flights that are significantly early. It's just hard to be an outlier. And again, if you're talking about an hour-long flight time, being more than 2 or 3 minutes early is hard. Okay, so there just aren't outliers to the left. There's not a real tail to the left. Okay, there is hard skew to the right, but strong skew to the right. Okay, and then what is a box plot going to look like? That's interesting. Sorry, let me make this markdown. And we can do a box plot for delay. And again, you can see that there are so many outliers that the box is kind of collapsed. And so, yes, are we seeing bell-shaped data? Not really, right? There's just so little tail to the left compared to this massive skew to the right. That no, I'm not going to call this approximately normal. We don't have approximately bell-shaped data. We do have this huge skew to the right and tons of outliers to the right. Okay. So again, I don't think we need to say anything more about the analysis. The box plot has just confirmed everything that we've found out earlier. Okay, so and let's take a moment to see what this third one is. Make sure that everything is loaded. The third one that they want us to do is the elevation data for Kansas airports. Okay, and Kansas is going to be KA. That's interesting. So let's go ahead and take the categorical variable, the descriptive statistics. All right, so this is number 3, Kansas airports and elevation. Okay, the elevations of Kansas airports. And what do we find out? Well, I have to change all of these to KA. The MAs in this that I copied need to become KAs. And I'm need to change the print statement, right, for number summary for elevation. At the moment, I'll just call it elevation. We know we're talking about elevation data, specifically from Kansas airports. We did this subsetting, or the subsetting was done for us. And what do we see here? Okay, so let's look at Rob's rule of thumb, and we look at the difference between the mean and the median, which is what, 250, 257, okay? And a standard deviation is 732, so a tenth of a standard deviation is 73, and oh my yes, it looks like this is skewed right. Okay, interesting. And we would expect outliers to the right. So let's go copy paste that outlier block. I'll get it from here. Okay, and so when we look for the outliers, and remember this is KA, so let me copy paste that. And I want all the delays to become KAs. And remember there's a couple over here. We have to scroll over and make sure we get all of these over here. And coming back, delay becomes KA there and there. And for Q1, and I think I have them all. I'm just looking to see that I've changed. Oh, there's a delay that needs to be KA. Okay. Believe I have them all. And again, we have 33 outliers to the right according to the 2 standard deviation rule. And we have 44 outliers to the right using the box plot method. And I just want you to notice this is true. The box plot method tends to identify more outliers. It's a little more liberal in identifying outliers. In other words, if it's on the borderline, the standard deviation method might not identify it as an outlier, but the box plot method is picking up those sort of marginal outliers. Like, is it an outlier? Is it quite an outlier? Well, the marginal ones, the box plot is going to pick up a few more of them. And it's not bad that we have 2 different methods that disagree sometimes. They largely agree, and think about how do you identify an outlier in a multivariate setting? What if I have multiple variables? How are you an outlier on multiple variables? Does that mean you're a strenuous outlier, a strong outlier on 1 variable? Does that mean you're kind of a moderate outlier on 3 or 4 variables? So there are a lot of question marks about how to identify outliers. in modern statistics. So this is not a bad thing. We've got two different methods we're using. We're comparing and contrasting what they say, and that's a very modern approach to outliers. All right. So our analysis is similar to before. We're going to say we have skew and outliers to the right. Again, you got to remember that this analysis is just suspicion, right? We haven't seen the shape, right? So this is suspicion. And let's look at the shape, all right? So shape for the elevation data. Okay, and remember these are Kansas airports. So let's do a density plot first. We've always been looking at the histogram first, but let's try a density plot. I will mention that you'll see when we get onto t-test, we do use these density plots a good bit. What am I seeing? I am seeing a tail to the left. I'm seeing a longer tail to the right as we suspected, and I am seeing nicely bell-shaped data, right? I have the majority of the data here around 900 to 1,600 feet above sea level, which makes sense, by the way. Dahlonega would fit in that, right? We're about 1,100 feet above sea level, depending on where you are in the county or the city. And so this is Kansas. The surprising thing might be this. And fair enough if you found that a little surprising. There are some hills in Kansas. Not very many, as you can tell from the graph, but there are some. So there are a few airports and heliports that are at 3,000 feet elevation and amazingly at 4,000 feet elevation. I honestly didn't know that Kansas had anything that high. Okay, so let's see what the histogram will tell us. And the histogram tells us largely the same thing. Let's add breaks equals 20 just to see if some more bars help. And no, more bars give us a little more granularity so that it looks similar, right, to our density plot. Again, the big advantage of the density plot is the granularity. And again, with more breaks, it hasn't destroyed the bell-shaped look early in the graph, right? It hasn't destroyed this look at the left-hand tail that is emerging. It's not very big, but you can definitely see it. So we're seeing the bell shape and we're seeing the skew to the right. Okay, bell shape, skew to the right. And that's pretty much our analysis after seeing the descriptives, the outliers, and the density plot and the box plot, right? We're going to have an analysis that this is approximately normal data with a strong skew to the right. It is. I mean, if you just want to look at the box plot and we can count, right? If you look at these tallest bars in the middle, right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bars in the right-hand tail, and I have 1, 2 bars in the left-hand tail. And remember, the bars are always the same width. That bin width is identical for every single bar in a histogram. So we have a right tail that's 6 times longer than the left tail. Do we have a left tail? Yes, barely, right? But we do have a left tail, and that's why we're going to say there's a strong skew to the right. Okay? Because there is. There's a couple of ways to see it, but visually speaking, yes. After we verify that there is, in fact, a visible, legitimate tail to the left, then we realize, oh, we have a much longer tail to the right, but we do have this bell-shaped data. Approximately. Again, approximately is doing a lot of work in that sentence, but we have approximately normal data with strong skew to the right. And let's do one more thing here. And let's do a box plot. There we go. Box plot, KA. Oh, and this wants to be Markdown. Okay, and so now the box plot confirms exactly what we've been looking at. There is strong skew to the light, right? Again, you see massive amounts of outliers up here, no outliers to the left, which makes sense. We're talking about elevation data in a state where a lot of the territory is between 900 and 1200 feet above sea level. Again, that's just how things are in the middle of the country. And it's hard to get lower than that. You know, we don't have a Death Valley type situation where we have some ground that's below sea level. You know, we don't have a Grand Canyon. We don't have a big dip in elevation below 900 feet above sea level. So there's no way really to have any outliers down here. Um, and so we're seeing this bell shape, and again, the middle 50% with the median a little lower in the box. But yeah, that's our bell-shaped data with less of a tail to the left, and then this huge tail to the right. So we've just confirmed, right? We didn't dispute the bell-shaped nature of the data, but it has this strong skew to the right. So there we go. That the analysis that we did after the shape is conclusive, right? We've decided now that that's what we're looking for. That's what we found. And so hopefully these three examples will give you an idea of how to work through this. We look at the descriptives, we look at the outliers, we look at a density plot, we look at a histogram, we look at a box plot. And from all of those things, we get an idea of the shape and we get an idea of the skew or outliers, if any. That's what we're reporting. Is it bell-shaped? And sometimes it's not. I mean, not every data set is bell-shaped. We use a lot of bell-shaped data in this course. Why? Well, they're good for the examples that we need to do with t-tests and ANOVA and linear regression and so forth. So yes, a lot of approximately bell-shaped data does show up, but you got to be careful. It's not always bell-shaped. Okay? And I'll see you soon with some more content.